Hello Matrix, welcome to yet another video, and this time we're going to be looking at physical sciences paper 2, that is the chemistry. So we are at the apothecary and we are to make our concoctions to try and see how we survive in this world. Otherwise guys, I hope you have written your paper 1 very well and that your spirits are high enough to then switch gears to preparations for paper 2, which in most cases is much more approachable than paper 1. But there are some questions that are famous for trouble for students. So thankfully this paper is packed with quite those kind of questions. So we're going to have a look at them and find a way of trying to gain some understanding on how we should be doing this. So I hope you guys are going to like it and that you're going to enjoy it. Otherwise, this is my way of waving my goodbyes to you guys for the year 2022. So this is definitely my last video that I'm going to make in this year for you guys. I hope you've been enjoying the others as well and that you're going to use them effectively, as well as any other resource that is available to you. Remember, if you do not do your own part, which is to sit and consolidate on these, just watching is not good enough. So watch to gain understanding, to see the ease or at least the method of going about doing your work, and then you put it to practice and you see how you fare. Then after that, you will find yourself a very stronger individual, okay, within you. All right, guys, I've taken this one from KZN. It is literally a quite interesting paper, I can assure you. But please do make sure you revise also the exam of May, June, as well as November 2021. So if you've done those 3 papers, the November 2021, the May, June 2022, and take this trial as the 3rd paper, then you can do whatever else you want in between to ensure that you're well prepared. Okay guys, let's not waste time. I'm already losing it. So general instructions cannot be overly emphasized, and of course pay attention to local instructions. Otherwise we're going to start our steam train. Now we're told here 1.1, which one of the following is the functional group of esters? So what are we looking for? The functional group. And of what compounds? Esters. Okay, so well, we know for a fact that we always have this situation where there's a carbon that is double bonded to oxygen and then one that is bonded to some carbon chain. All right, so this is an alcohol group. This one usually is for aldehydes. Okay, and then of course this one is more likely to be that of esters, and the Cu is for carboxylic acids. So here you don't want to stress, you just go for C, because esters have this double bond to oxygen and a single bond to oxygen, and there would be another carbon, and then of course that one goes to another carbon chain. So if you put this one in a condensed form, then you will see that you're getting that. Okay, so of course this one still has its chain, which is the carboxyl group. Is it carboxyl? No, it comes from the alcohol, so it becomes an alkyl group, and here this one becomes the carboxyl group. All right, not a problem. Ish, I'm already talking too much and not necessary. So some easy questions, you just go fast on them. Now, an organic compound is incorrectly, how is that situation over there? It is incorrectly named as 4,5 dibromo 2-ethyl hexane. Now the correct IUPAC name for this compound is Now you wouldn't be able to guess, so you need a structural formula of what is provided. So let's attempt to do the structural formula. So we can see that the parent chain here is a hexane, so it's an alkane. So we're going to say 1, 2, 3, 4, 5, 6. So there are no double bonds between the carbons, okay? And then of course we are told here this is 4,5, 2 ethyl. So on the second carbon we have an ethyl group, so which is going to be CC. Okay, I'm not gonna really do the hydrogens, I'll just use these little things here. So now there has to be 4 of them. Okay, then we're saying this is 1, 2, 3, then 4. We want the bromine here, and then of course there will be another bromine here on the 5th carbon, and we will see that then the rest is going to be hydrogens, hydrogens, then hydrogens, and then of course what is that? Hydrogens, hydrogens, hydrogens. Okay, now you can fill them up if you want, which is really not necessary. But why not do something about it when you can? All right, so this is the structure that is proposed here. So we are told this is 2 ethyl. So you see that is the ethyl group. So because we have 2 carbons, all right, 2 ethyl. And then of course we're looking at the dibromo part. So there is a bromine over there and another bromine. So of course this is under the premises that this is the first carbon and then this is the 6th carbon. So 1, 2, 3, 4, 5, 6. So we're making this one our parent chain. Okay, so what do we have here? Now let's see, we were told that this is an incorrect. Why is it incorrect? So let's explore what went wrong here. Now imagine you have to first remember the IUPAC naming dictates that you look for the longest chain first. Now what is the longest chain here? Look, there's 1, 2, 3, 4, 5, 6. So this is the 6. Now let's look when we take out that branch. 1, 2, 3, 4, 5, 6, 7. So do you see the longest chain is basically starting from here or there, but you see it's the L. Okay, maybe let's use let's use some color to show it. So that becomes the longest chain. Okay, so if we make that the longest chain, because I mean not that we make it, but it is so. So there's 7 carbons, so it's a heptane. So anything that says heptane is correct. So we can already eliminate those 2 options. So now we have to dangle with these 2. Which one is correct? Now if we look here, now we have to decide where do we go. So remember, this is a haloalkane. So if we say haloalkane, we have to think about the functional group. What is the functional group of haloalkanes? We need to see those bromines. So the closest distance to those bromines, which identify this one, we have to think about it as a haloalkane. And then again, if you didn't want to prioritize the functional group, so to speak, in essence, these could be regarded as side branches, but then you go in alphabetical order. B comes before E because this is the ethyl, what is that? The methyl group. So this becomes a methyl group over here. So meth, B comes before M. So you would still have to think about it. So this is the first carbon, second, third, fourth, fifth, sixth, seventh, okay? And then now we're going to say this is going to be 2, 3 dibromo. So we can already see that, son, you know what? Now this one, already starts by doing the right thing. It doesn't say 5,6. All right, so already this one is out because of that. I mean, the rest is just, anybody's guess. So this is 2,3 dibromo, because there's 2 bromide groups, and then this is 2, 3, 4, 5. On the 5th carbon we have a methyl group, so this is 5-methyl heptane. So this tells you and I that we now have sorted this question here. So I know I've taken longer than I'm supposed to. Some questions need a bit of time to think about, because it can't be this. All right, it can't be this. You can't start. I mean, again, you think about it. What is the closest distance to the side group, if you think of these as side groups? If you're saying this is the first carbon, second carbon, this methyl group would be on the 3rd carbon. But what about the bromine? It's right on the 2nd carbon. So you go choose the closest distance to the side branch before you can go to the one with the longer distance. So B is definitely our answer. Okay, let's move a bit quicker. 1.3, which one of the following compounds has, what is that? Okay, 1.3 says, which one of the following compounds has structural isomers? Okay, meaning you can vary the positions of certain atoms in the structure. Now, if you put the chlorine there, it's still on the 1st carbon. If you put it here, it's still on the 1st carbon. If you put it here, it will still be on the 1st carbon, because this is a symmetrical. This is a symmetrical molecule. So definitely changing the position of that chlorine group doesn't place it in any other carbon but on carbon 1. So this one, not possible. Now B, we look at this one again. We have a symmetrical molecule there, or should I say compound. If we change this Br into any of these positions of the hydrogens, it will still be on the 1st carbon. So that one is also out. Then if we look here, if we change, say, the chlorine and put it over there, it will still be asymmetrical, because we'll have 3 chlorines on this carbon and then 2 on the other one, like it is the case. So even this one doesn't help. Now this leaves D. But why is D correct? If you think about this situation, if you take this bromine group and put it here, do you see now there will be 2 of them on the 1st carbon? Then it is the case here, where there's 1, 1. So if you have 2 of them, there's definitely a variation of this molecule. So that is why it will have a structural isomer, or even structural isomers. Okay, but again, I mean, you can only add 1 bromine each time. So that is the story. All right, so let's get to 1.4. 1.4 says, the graph below shows the change in potential energy for the hypothetical reaction. So we have 3p, which is a gas, a diatomic gas, plus Q, which is also a diatomic gas, going to P3Q, which is also a gas. And we are told that our delta H is negative. So this is what? An exothermic reaction. How do you see that on the graph? You will see that the reactants would be here, and then the products would be there. So what do we see here? The energy of the reactants is definitely higher than the energy of our products. So this tells us that this is definitely an exothermic reaction, which concurs with our delta H. Okay, so what do we know about this situation? We know that, well, for the forward reaction, the activation energy would be this one. No, for the reverse reaction, basically, because it's starting from the bottom. So when we reverse this becomes reactants, and those are products. So the activation energy for the reverse reaction is that. And what is it in the value? The value they're giving us is 100 kilojoules. So we know that from here to the top there, it is 100 joules. Okay. Now, what else? What is the activation energy for the forward reaction? Of course, for the forward reaction, it starts from the reactants, sort of, and then it goes to the top. So maybe let's use a blue color. So the forward reactions activation energy is going to be that. Okay, so forward reaction is the blue one, the reverse reaction is the purple one. All right, now what is this difference between the reactants and the products? It's 40 joules, kilojoules, sorry. So we know that, well, this line is basically minus 40, so we can just simply say 40 kilojoules. Okay, I don't know if it's gonna work. Okay, yeah, I did try. So it's 40 kilojoules. All right, not a problem. All right, so what does it tell us? It tells us that, well, we can also consider this scenario here, that this activation energy here is going to be essentially, what is that? The total here is 100 minus 40, that becomes 60 kilojoules. Okay, so always try to work your diagram when you are given one, because it makes your life a bit easier. I mean, there's nothing more we can do at this point. We just leave it alone. All right, so the question says now, which one of the following could represent the activation energy of the forward reaction when a catalyst is added to the reaction? Okay, so this one, so this one says, remember, when we add the catalyst, we lower the activation energy of the forward reaction. So this means with the catalyst, we'll have something like that. Okay, so that means we can lower that activation energy for the forward reaction. So this is a catalyzed reaction than the one that takes place on its own. So do you see what was the activation of the forward reaction? It was 60. Okay, it was 60 kilojoules when we did the calculation. It was not necessarily given, but we had to determine it. And then now what we know is when we catalyze this, it definitely will be something less than 60. Okay, so we can already say that 60 is the standard. We don't take it, we don't take that, but we know that that is correct. So our answer becomes A, because 50 kilojoules is less than 60, which was the original activation energy. All right, so let's keep moving. Now we have the balanced equation below represents the decomposition of calcium carbonate. Okay, so we can already see that this one decomposes to calcium oxide solid and carbon dioxide gas. All right, so not a problem. And then now we're told you which one of the following volume time graphs represents the formation of carbon dioxide. Okay, remember when this starts decomposing, we have a higher concentration or a higher amount of calcium carbonate, while we have none of these two. But as the reaction of decomposition starts happening, what happens? This starts forming and that starts forming. So the formation of carbon dioxide increases at the beginning. So yes, it starts from 0 and increases, but does it increase in a linear fashion? The answer is no, it doesn't increase endlessly. But over time, we're getting less and less of this. Now, as we start to have less, then there will be less of this one forming. So it kind of plateaus as the reaction proceeds until completion, when it is exactly flat at the top. So this one looks like a good candidate for the answer. And then here we are told that there's a decrease. No, it doesn't start from a higher value to 0, not at all. It starts from 0 to something, and then it stays as something once the reaction stops occurring. This one also is wrong, because it's saying we're starting at some value, and yet we know that we're supposed to start at the origin. The starting point is good and the end point is good, so the answer here becomes B. Okay, so no problem over there. So let me just drink my Coke. Okay, so let's keep going. So the next question says, consider the balanced equation below. And remember, MCQs, you must make sure you finish them within 30 minutes at least. In fact, 15 minutes if you can, or 20 minutes if you really want to push it. Now consider the balanced equation below. So we have nitrogen gas plus hydrogen gas giving us ammonia gas. This is the Haber process, and we are told the forward reaction is exothermic, meaning it releases heat. So there is a plus heat sign here, which is usually never really indicated. Okay, now the graph below shows a change made to the system at equilibrium in a closed container. And then of course, why is this system in equilibrium? Because we can see that the rate of the forward reaction is equal to the rate of the reverse reaction, because those arrowheads are exactly level with each other. Okay, now let's look at the situation. And then they're saying the graph below shows a change made to the system of equilibrium at time t1. Okay, so look, the system was already in equilibrium from the word go, but of course it doesn't mean that it started at equilibrium, but we captured this graph when it was already at equilibrium. You can see those are parallel to each other. So once you see parallel lines like that, this already tells you you are in equilibrium. And then we can see here at T1, our time of interest, there is a sharp rise on the concentration of the hydrogen gas. Okay, it sharply rises, where there is a gentle rise on the concentration of our product, which is the ammonia gas. So our ammonia gas is our product in the equation, so it slowly increases. So whatever happened here that resulted in the sharp rise of the hydrogen gas effectively favored the forward reaction in essence, so that we formed more of the ammonia. Okay, but now what happened? As we keep forming more ammonia, we know that we're going to be expunging our nitrogen gas, and that's why it slowly decreases. Okay, so now again at around this point over here, we can see that we are almost flat again. So we've established a new equilibrium. Again, okay, so that is fine. So that's a new equilibrium. All right, so what could have happened here? Look, the only thing that makes sense is that this sharp rise would tell us that, look, we may have added more hydrogen here, so that more of it took some of this one, and then hence we get to that. Because if it was a temperature, remember temperature favors the reverse reaction, so we would start to actually lose the ammonia that we formed, and then would start forming more. So there would be actually a gentle rise on this hydrogen and the nitrogen, while there is a decrease on this one, if that was a temperature change. Say an increase in temperature. But a decrease in temperature would essentially favor the forward reaction. But what happens is this one would slowly, in fact sharply decrease rather than slowly. It would sharply decrease, and this one would sharply decrease, and then this one would be forming slowly over time. Okay, not a problem. And then of course the rates of the reaction, once you decrease the temperature, they would actually change. But concentration time graph doesn't really capture that at this point. Yeah, pressure, there's more gas molecules on the left than on the right. So if we increased pressure, we would sharply rise this concentration for the hydrogen as well as for the nitrogen. There would be a sharp rise for the two, but now it's not happening simultaneously. So it can't be a pressure change. So it's definitely an amount that was added to the system. Now it says, which one of the following changes was made at time t1? A catalyst was added? No, because if the catalyst was added, we'll just simply see a gentle rise on this one with a gentle decrease on the reactants as well, like it would be the case with temperature sort of. Anyway, the volume of the container was decreased, meaning pressure was increased. Again, we saw that pressure could not do it, because if it was, we would also see a sharp rise, in fact, on all of these initially, then with this one maintaining a gentle increase while these ones start slowly decreasing. So a temperature of the container was increased. If we increase the temperature, we're favoring the reverse reaction, then we would see this one decrease with these ones increasing. So not true. So none of these are true. And it leaves us just one answer. D. Yes, it definitely was added. There must have been an addition of more hydrogen gas into the system. All right, not a problem. So that is easy. 1.6 is as we see it. Okay, let's try and get to this answer quickly. The products formed during the hydrolysis of sodium ethanoate, okay, are, now you look here, is it sodium and hydroxide ions? Well, remember, sodium ethanoate is kind of a basic salt, okay? It's kind of a basic salt because the ethanoate ion is a weak base, all right? So when it gets into water, what water will do, it will actually protolyze the ethanoate ion to form ethanoic acid. All right, so if we form ethanoic acid, what happens? The water releases the hydroxide ion, so it's going to be the hydroxide ion as well as ethanoic acid, because sodium is purely a spectator ion here. So anything that tells us about sodium is definitely not helping us, because this is a spectator ion in this case. So the oxonium ion and the ethanoate ion, the answer is no. We're not necessarily going to form the oxonium ion, but the acid itself, the conjugate acid for this. So what is the story? It is going to be ethanoic acid and OH minus. So I think that's the best answer. So it can't be this one, but most likely that one. Okay, so we have 3 minutes, guys. So let's move. We don't have time to waste here. Now the question says, which one of the following aqueous solutions will have the lowest pH? So remember, lowest pH means the highest concentration of the oxonium ions, or you guys call it the hydronium ion, which is fine. Anyway, so if you look here, hydrochloric acid, it's a monoprotic acid, so its concentration will effectively be the same as the concentration of the oxonium ions. So that's quite a higher concentration, so it's something to consider. Maybe let's not correct, but we can say, yeah, something to consider. Put an asterisk. Sodium hydroxide, it's already a base, so this one is out, because a base, it's a strong base even, so the pH will be greater than 7. So the sulfuric acid, remember this is a diprotic acid, so meaning it releases 2 molecules of the oxonium ions. Now that means the concentration of the oxonium ions is double the concentration of the acid itself. So this one will release for us the concentration of oxonium ions that is essentially double that number, which is 0.4. Okay, I don't know what is happening here. Okay, and then now do you see 0.4 unfortunately is now bigger than 0.3. So that means this is the one that is more likely to form the lowest pH. Otherwise, ethanoic acid is of the same concentration as that, and we know this one ionizes partially, so the concentration of oxonium ions is even less than would be the concentration of the oxonium ions coming from the hydrochloric acid. So this one is out, so our best answer is C. Okay, let us move on. Now we deal with 1.9. Okay, what is the story about 1.9? I'm taking time, which is not allowed. Okay, the salt bridge of a galvanic cell. What do we want? We want information on the salt bridge. Now it allows electrons to flow through it. Does it allow electrons? That's a good question. Well, I don't think so. The answer cannot be allowing electrons, because electrons flow in the external circuit, meaning in the connecting wires between the two electrodes. But in the solutions, we only have ions moving to complete the circuit. So it's not electrons, but ions. So it's only ions that flow, in the salt bridge. So not electrons. It allows anions to travel to the cathode. Remember, the cathode loses positive charge, right? Because we're taking positive ions and reducing them into a solid. So if we lose positive charge, then we need positive ions from the salt bridge to go into that solution of the cathode to neutralize the situation, because it would have a negative. So it cannot be anions, but it has to be cations. Okay, or cations. Okay, now it says allows cations or cations to travel to the cathode. Well, that sounds correct, because cations are the ones that we're losing by the reduction that is taking place at the electrode. So we need to neutralize that situation by adding cations there. So C sounds correct. It provides ions to react at the anode and cathode. Well, I wouldn't be too sure about the word react, but they help to neutralize the situation. So I wouldn't really say reacting, but rather to neutralize, because we will have excess of negative ions as well as excess of positive ions on either solutions as we lose what we lose. Therefore, we want to add those ones to kind of neutralize, but not necessarily react. Okay, so I wouldn't go with this one of reaction. So my best answer there is C, but at times you may find yourself unable to decide between the two, because it makes a bit of sense, but I could not be too sure of that one. So these are some of those questions that may give you a bit of a headache. 1.10. Please don't ever read this by saying 1.10. Okay, there's no such a thing. I mean, please guys, try to be scientists. Don't be, not that we have to disrespect people who didn't go to school and didn't do science and all that. But don't be like, people who did not have an experience of learning science. So be scientific about just about anything, however insignificant it may be. You just want to maintain the science. All right. So this one, excuse me. So this one says the simplified diagram below represents two electrochemical cells. Okay. Remember, electrochemical cells is a non-specific word, since we know that we have two types, the galvanic cell as well as the electrolytic cell. Okay, using electrolytes of equal concentrations. So what about these electrolytes? The electrolytes have equal concentrations. Okay, we're not told though that the electrolyte is the same. All we know is that they have equal concentration, as well as identical batteries. So we have two cells. All right, identical in that they deliver the same amount of energy. They probably have the same amount of internal resistance. Okay, not a problem. So we can see there that the first one uses copper chloride solution. This one uses silver nitrate solution. Perhaps if you ask yourself, why not silver chloride? It's because silver, when it meets chloride, it forms a precipitate of silver chloride salt. And that will effectively form a precipitate, and that would mean it cancels out these ions. So therefore we need these free ions to move so that we can complete the circuit. Otherwise, once these ions are taken out of this solution, then we will lose the conductivity of this liquid here, meaning there would be no conduction of electricity, and that effectively would stop doing whatever we needed to do. Okay, so please understand those things. You know from grade 10 which type of salts are insoluble and which ones are soluble. Usually all nitrate salts are soluble, so this one is soluble. Now, the electrode that shows the largest increase in mass per unit time, okay? Now, the electrode that shows, we want the largest increase in mass per unit time is. So which one of these is? Okay, now, if we look here, what is going to happen? Of course, the negative terminal, remember the positive is the anode, the negative is the cathode. So this is between F and H because it's only the ones that are connected to the negative terminals that have an increase in mass. So already here you know that E cannot be, and you already know that G cannot be. So the answer is between F and H, because the ones that will show an increase in mass are the ones that are connected to the negative terminal of the battery, which is the cathodes. All right, now look at this, guys. So what happens is, remember the copper goes, not the copper, but the chloride ions, they become oxidized into chlorine gas. But between the two, we know that these copper ions are very weak reducing agents, all right? Meaning their oxidation ability, their ability to go into oxidation is very weak. Hence, we needed a battery to get that to happen. And copper is itself a very weak reducing agent. But, it's quite a strong oxidizing agent. What am I saying? And this one will kind of readily be oxidized. Sorry, did I say oxidizing agent? Will be kind of readily reduced to copper solid. So technically we'll be forming copper in this electrode. So copper will definitely be going into forming a copper layer on this electrode. Usually we use these electrolytic cells to electroplate, meaning to coat another metal with yet another metal to try and resist issues of desiccation or even a look that is appealing and things like that. Okay, so this one is fine. So what is the story here? We know that copper accepts 2 electrons, okay? So now we will add 2 electrons basically in here. Okay, so the number of electrons will tell us exactly how much mass is going to be piled up onto this one. So here we know that copper will take 2 electrons to get to that copper. So there's 2 electrons that are added to copper to get into copper solid. But now what will happen here? Now we know that technically silver is the guy that is going to try to go there. And what will happen here? We know that, well, this friend of ours here is not quite in fact, this guy here neither goes and doesn't do in fact, it cannot be oxidized because it is itself a very strong oxidizing agent. So it tends to become reduced to nitrogen monoxide gas rather than be oxidized into something else. So if you look at the standard electrode potentials, you'll see that if we look just through this nicely, I don't like to do this back and forth, guys, but it's happening and I have no control of it. You yawena kanti zingaphi izinto ezi ngathi ndisengxakini nje. Now if you look here, look at the nitrate ion, look at that. First of all, this one takes 3 electrons to go to nitrogen monoxide gas and a water molecule. And then here we have another nitrate ion. Do you see it gets reduced? They are both being reduced, but this one gets reduced to nitrogen dioxide gas and water molecule. And then of course these are acidified reactions. You have to add some acid there to happen, to get this to happen. So you can already tell that these ones need a lot of help before they can do stuff. But we don't see the nitrate ion appearing on the right hand side, and it does not go that way. So it means that one cannot undergo oxidation. So wait a minute, what am I doing? So now which one? Remember we had an aqueous solution, meaning that AgNO3 is in water, Baba. So this is in water. So can water now be? Yes, definitely it can. If you look here, for example, where is the water molecule? If you look at this water molecule, 2H2O can actually be oxidized to hydrogen peroxide and hydrogen ions, okay? That is true, but now we don't want something that goes there to hydrogen peroxide. Look, there's another one here. So you always look and check which one is going to be favorable. We know that when we oxidize water, we release oxygen. So sometimes it helps to know what will be the product of doing something, So we know that usually when we oxidize water in redox reactions, we release oxygen instead. So we don't really look for the one that releases hydrogen peroxide. So water can be oxidized into, but look at the amount of electrons that are released. It's 4 electrons versus the 2 electrons copper accepts. So can you see that this amount, it tells us that there's going to be quite a larger mass for that second cell than on the first cell. So if there's more electrons being given off, then that one will register a larger increase in mass. Okay, so yeah, I've taken longer than I planned to, guys, but I started talking anyway from the very beginning, so it is what it looks like. So basically that is going to be H, right? Because there's more electrons going in there. So there's going to be here plus 4 electrons from the water molecule being oxidized, because this one cannot undergo oxidation, the nitrate ion. Okay, so I hope that makes sense, guys. So this one becomes less because it only gets 2 electrons, so not so much of a mass is added there. Okay, guys, let's quickly get to question 2, which is the nice one. Question 2 is cool. Because this is where you just enjoy yourself. So we have a name. Once we have a name, it's much better. So this is 4-ethyl 2, 6-dimethyl hept 3-ine. So this is an alkyne, basically. Okay, so this one is CH3CH2CH3. So this looks like an alkane. It's definitely an alkane. It's 1, 2, 3. So it's propane. So let's see what homologous series this is. So this is C3. Now how many hydrogens are here? 6 plus 2 is 8. Yeah, this is definitely CnH2n plus 2. So this is an alkane, which is propane. Okay, let me try to write properly. Alkyne. Okay, so that is it. And then to be more specific, it's propane. Okay, then we have here C5H10O. So what usually this is, once it is put like this, it's most likely an aldehyde, okay? But you may be surprised, but I mean, when we do this kind of a molecular formula, it can be quite confusing. It's better when we're doing a condensed formula, but a molecular formula like this is most likely an aldehyde. So we'll find out. Even ketones can be confusing, so it could also be a ketone. We don't know. And then this one, it's more or less the same story, but remember, this thing can be pretty much anything, so you don't want to think about it carelessly. I'm just trying to think of the homologous series. What are the formulae that we use to be sure what this is? Because if you know those CnH2n plus whatever, it helps a lot to understand what is going on. But anyway, let's not complicate our lives. It's most likely an aldehyde, or it could be a ketone. It could even be an alcohol. So even that one, it can be anything. So we move on. E, we can see here clearly that this is what? If you have the carbon that is bonded to oxygen, is basically a secondary carbon because it is bonded to two other carbons. Then this becomes ketones. So this is a ketone. And then this one, once you see the OH here, this is an alcohol. Okay, we don't know which one, but it's an alcohol. So the question is, what is that and what is that? I mean, this could be even this one. It could be a ketone as well. Okay, so I kind of forgot the homologous series, how they work. I never really paid attention there. So anything is possible. Even an alcohol still could be that one. So, you know, there's a lot of things, but let's just not waste time, because sometimes it may not even be necessary. Now use the information in the table to answer the questions that follow. Now for compound A, write down the general formula of the homologous series to which it belongs. We said this is an alkyne. That suffix YNE. So this is alkynes. But now they said the general formula. The formula here is okay, let's just try to answer properly here. So this is 2.1, 2.1.1. So we have 2.1.1. So we know that these are alkynes. So this is CnH2n minus 2. That is the homologous series. So 2.1.2 says the structural formula. So let's look at this one. What is the parent chain? Is a hept3-ine. So we start there. So we have a hept3-ine. So hept is 7 carbons. So this is 1, 2, 3, 4, 5, 6, 7. So make your life easy. Just choose a straight chain. Now we have 3. So this is 1, 2, 3. So on the third carbon, we have our double bond. Our triple bond. So remember, when you say 3-ine, it means the triple bond is between the third carbon and the fourth carbon. We always use the lesser of the two as the signature for, as to on which carbon is this sitting at. So we are sorted with our parent chain at this point. Now what do we want? We want to do 5-ethyl. Okay, 5-ethyl. So already we know that this is the third carbon, so we can't be coming from this side. So this is 3, 4, 5. Okay, so on the fifth carbon we have an ethyl group. Okay, so we have 5-ethyl and then 2,6 dimethyl. So on the second carbon we have a methyl group, and on the sixth carbon we have another methyl group. Okay, so we have a dimethyl hept 3-ine. Okay, 2,6. Let's be sure. This is 1, 2, 3, 4, 5, 6. Yes. Okay, now everything else is sorted. Now we can do our additions of hydrogen. So 1, 2, 3, 4. 1, 2, 3, 4. So this one only gets a hydrogen. So you cannot say this is complete without the hydrogens. What is that? Here when I'm doing a crime now. That is the bond to that methyl group. Okay. So where else? Here. Then of course we need another, and then another. All right. So okay, so that is how complex that structure is. Just make sure everything is in order. Just make sure everything is in order. You get a mark for placing the double bond. I mean the triple bond where it's supposed to be. And then you get a mark for the entire structure. I mean maybe a mark for the methyl groups and then a mark for the ethyl group's position. So that is how you get your 3 marks there. All right, easy. 2.2, but of course it takes a bit of time. So let's answer 2.2 quickly. So we're going to have 2.2.1. So what is the question here? It says now compound C. So where is C? It's this one that we're not sure what it is. Okay, not a problem. Now it says is a functional isomer of compound E. So now a bit of extra information at times helps. So what is a functional isomer? It's, a compound that has the same molecular formula as any other, but they belong to different homologous series, or functional groups. So look at compound E. We can see that this is a ketone. So definitely ketones and aldehydes are functional isomers. So definitely our friend here is our aldehyde. At least it helps us. But if we had to, we were going to draw the structure that is possible here, and then we would know what it is anyway. So I told you, define the term functional isomer. Okay, not a problem. So, okay, now these are molecules or compounds. Let's just say these are compounds. Compounds with the same molecular formula, but with different, or say belonging, but belonging to different homologous. Homologous is not correct. Series. Okay, but you can also say they carry a different functional group. Okay, so that is it. Not a problem. So you get your 2 marks there. Is it a 2-mark question or is it a single mark question? Yeah, usually definition 2 marks. So don't lose marks. So it says now write down the IUPAC name of compound C. Okay, 2.2.2. Now for us to know the IUPAC name, we already now know it's an aldehyde. So aldehyde has the double bond of oxygen on the last carbon, or the first carbon if you think about it. So there's 5 carbons there. We have to first do it. So if it is 5 carbons, I mean this is pentan. And then of course aldehydes end with an Al, so it's pentanal, so we don't have to worry. pentanal. Wasting time drawing that structure is not important. Again, if this is just a name, you get 2 marks normally, which is the case. Okay, so let's do 2.3. What is question 2.3 telling us? Now, we are to say now, compound D is a tertiary alcohol. So do you see? Compound D is a tertiary alcohol. So can you see? It's not very easy sometimes. So you've got to understand what is going on. Anyway, so tertiary alcohol, it means the carbon bearing, the OH group, is bonded to 3 other carbons. That's what a tertiary alcohol is. So 2.3.1 says name the functional group of compound D. Name the functional group. So it is the hydroxyl group. So 2.3.1, so it is the hydroxyl group. Great. So 2.3.2, what is the story? Here it says, now let's do the structural formula of compound D. So that's going to be a bit of work. So how many carbons there are? There's 5 carbons and 12 hydrogens and an oxygen. Okay, 5 carbons. Oof, this is going to be quite interesting. So how do we do this one? All right, so we're trying to make it as symmetrical as possible. I think if we make it symmetrical, it's gonna be 1, 2, 3, and then of course maybe let's do it like this properly. So the OH group is always split into oxygen and hydrogen like that. And then we have 1, 2, 3. So now we need 2 more. So for it to be tertiary, there has to be some branch here. So it's going to be an ethyl group. All right. Okay, so let's have a look here. We had C5. There's 1, 2, 3, 4, 5. And then H12. Was it H12? Yes, H12 and then oxygen. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, looks okay at this point. But yeah, there's many isomers of the same thing that you can do here. Maybe one more, but it's okay. Even if you did the isomer, as long as it matches a tertiary alcohol, it should be okay. So no need to sweat here. All right, so let's get to the 2.4 question. So let's do 2.4. What do they want? So compound F, okay. What is compound F? It is an alcohol. All right. Compound F reacts with propanoic acid. So it reacts with propanoic acid in an acid catalyzed reaction. So there is a catalyst, which is an acid, to produce a straight chain organic product. Okay, give the name given to this reaction. So what is the name of that reaction? Okay, now remember, it's not the type of reaction, but the name of the reaction. Now the name of the reaction, so 2.4.1, this is esterification. But if they asked the type of a reaction, you would say it's a condensation reaction. But sometimes there's a tendency for interchanging these. But I always pay attention to what the question says. So if it says the name of the reaction, it's esterification, but the type of reaction, it's a condensation reaction, which is a form of elimination reaction, so to speak, while you're condensing two other molecules. There will be some byproducts, okay? It's not a problem. So write down the IUPAC name of the organic product. Remember, when you're forming an ester, it carries the alkyl group from the alcohol, and you add the carboxyl group from the carboxylic acid. So what is the carboxylic acid? It's propanoic. So we're going to have a propanoate at the end. What is this alcohol? How many carbons are there? There's 4. So this is butanol. So it has to be a primary alcohol. So this is butanol, or butan 1-ol. So it's going to be a butyl or butyl. So 2.4.2. This is going to be a butyl propanoate. Okay, that is the name of the ester. So you start with the alcohol part, which is the alkyl part, and then you end with the carboxylate part of it, which is the propanoate ion. Okay, so I think we have sorted that one. So you're getting 2 marks for those 2 little portions of it. Just make sure though you guys are doing everything that is fine. So they didn't ask too many things, so you leave everything out. So remember, we're doing the final revision now, so you need to know a lot of the details, but at this point you don't have to sweat. So let's look at compound F. Wow, I actually thought I would have these answers here. So whoa, what is that? What is that? Yeah, Buffett, we need to move in this next hour, okay? So these answers were supposed to be there, so there was just unnecessary space left. Okay, so sometimes you over prepare because you're not sure how much time, how much space you're going to need. So let's quickly get to question 3. So this is the question on physical properties, almost always. So an investigation was conducted to determine the effect of one of the factors on the boiling points of alcohols. Okay, now 3 straight chains. Now what is important is to make sure everything is making sense. So 3 straight chain primary alcohols, P, Q, and R, were used. The results obtained are shown in the table below. Okay, you can see P there is actually ethanol. Okay, if it is a straight chain, ethanol, but it could be ethan 1-ol, can be, yeah, actually ethanol, because if there's 2 carbons, where that H is doesn't matter. It's a symmetrical molecule, so it's just ethanol. So we have 78 degrees Celsius there. Then Q is 5. So 5, yeah, it's a different story. This can be, propane. It can be pentan 2-ol, pentan 3-ol, you name it. But at the end of the day, it's a straight chain. So we have 117 degrees Celsius. R is a 3. So 3 can be propan 2-ol or just propanol. So it has 2 names there. So it doesn't matter which one. Now I told you, define the boiling point. Okay, but if you look here, the longer the chain, the higher the boiling point, because do you see here, C5 has a higher boiling point with C2 with a lesser boiling point, and we're just playing now, C3 with a slightly higher boiling point. Okay, not a problem. So define boiling point. All right, 3.1 is starting us on a nice lovely ride. So I don't know, will I have enough time to write things here? Maybe maybe not. We will see. Where did I start this one? So 3.5. So if I'm going up till 3.5, but I think I can answer these questions in this page. So we start here, 3.1. The boiling point is defined as a temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. Okay, so it means the atmosphere is overly saturated, just above the liquid is saturated with the vapor, so it starts boiling. Okay, so that is the story here. So it's the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. So this one is as simple as that. You get your 2 marks and you give no further regard to that question. So next question says, is this a fair investigation? You know what? Yeah, these are some of the questions which I went on. Is it a fair investigation? You know what this can be debated at times, but yeah, let's just look in terms of your curriculum. Your curriculum says, I kind of interpreted one of those questions during the May June exams as if I'm interpreting just any scientific paper, but you have strict guidelines on this one. For a fair investigation, you're told there has to be one independent variable here. And then, of course, which one is it here? Basically, is the carbon chain, okay? Because these are straight chains, so that is the carbon chain here. So it is definitely fair. Why? Because there's only one independent variable here. It's the length of the carbon chain. All right, so the answer is a yes. 3.2, we say a hell yeah. Excuse the choice of the word. Yes, you can say there is only one independent variable, okay, which is the length of the carbon chain, or you can say molecular mass. All right, not a problem. So it is definitely a fair one. So you get a mark for the yes and a mark for your little explanation. And then we are told here, okay, write down a suitable conclusion for this investigation. And then, of course, if we have our data summarized in a table form like that, we can already see that the higher the molecular mass or the longer the carbon chain, the higher the boiling point. So it doesn't really matter which one you choose here. So since we talked about the length of the carbon chain here, so we will say 3.3. We can say the longer, no, don't rush, the longer the carbon chain, the higher is the boiling point. Okay. So that is what you want to say, or you can say the higher the molecular mass, the higher is the boiling point. That's not a big deal, as long as it makes a scientific sense. Now it says fully explain the answer to the question in 3.3. So why is that the case? Now we get our arms flexing, 3.4. We can say their primary, this hand, alcohols have in addition to London forces. Maybe something is not supposed to be in here. In addition to London forces, hydrogen bonds. Okay, now what do we know is that the longer the carbon chain, the larger is the surface area for the action of intermolecular forces, making them IMFs, making them stronger. Okay, now that means more energy is needed to then separate the molecules. Okay, I'm just trying to simulate your exams, guys. I mean, I know my writing is not the best, so please don't cry about it. I cried and stopped a long time ago, so even my teachers failed to change it, and they just had to see it. Somehow they did, because it never really compromised me. But don't be like me. Try to be as legible as possible. So I think here, the primary alcohols have, in addition to London forces, hydrogen bonds, which I think is a significant story. Now, the longer the carbon chain, the larger is the surface area for the action of the intermolecular forces, making them stronger. Even the London forces become stronger as a result. Therefore, more energy is needed to separate the molecules, and that's why we see an increasing boiling point. This results in a higher boiling point. As the carbon chain, I'm not going to write too much now. Now this results in a higher boiling point as the carbon chain increases. So this, I think, is a full explanation for what is required from us. Okay, so let's keep moving, guys. Hey, we are staying for too long here, and we should not. Okay, so the next question says, okay, let's start here. It's already copied here. The investigation is repeated using half. Okay, what are we using now? Half the original volume of the alcohol R, while keeping all other conditions the same. How will this change affect the boiling point of alcohol R? Choose from increase, decrease, remains the same. So obviously it will remain unchanged, right? Because it's the same alcohol, even though we took a small volume, but it still has the same characteristics, so nothing is going to change. So we get our 1 mark. All right, which one? Of course, don't highlight on the question paper, write it down, but I don't have time now to do that. So which one of the alcohols has the highest vapor pressure? So we know that the one that has the highest vapor pressure is the one with the lowest boiling point. So which one there is the lowest boiling point? It is, it's P. Okay, so it's alcohol P. So let's choose P, so we know that it's gonna be P. Now give a reason for your answer. The reason literally says because it has P has the lowest boiling, what is that? Boiling point compared to the others. Okay, so P has the lowest boiling point compared to the others, so it means this one will quickly evaporate and form a higher vapor pressure than the others. Okay, evaporation. Oh, we were asked that definition in standard 3. What is evaporation? What is condensation? Yo, what is climate? Man, yeah. Sibuza ngombethe, residue, ewena xelela. Nangicela ukudlala kule minyaka, nisafunda izinto serious. Anyway, 3.7. How will the boiling point of a straight chain compound, what is that? So let's investigate that molecule. C6H14, so this is the same as C2H2N plus 2. So that's an alkane, so straight chain alkane. So we know that we are dealing with an alkane, okay? Or this is effectively hexane, compared to that of alcohol Q. Choose from greater than, less than, to equal to. All right, so let's see Q. How many carbons does it have? Q has 5 carbons. Okay, this one has 6 carbons. Okay, it doesn't really matter, but what matters now is that they are of different functional groups. Okay, now choose greater than, less than, or equal to. Well, my answer here is going to be the boiling point of methane is definitely going to be less than. All right, now it says fully explain the answer. Okay, that question is always there, so we can say compound Q has hydrogen bonds in addition to London forces. Okay, it has stronger, maybe let's just put it that way. Let's not be careless here. So Q has strong hydrogen bonds in addition to London forces. Okay, in addition to London, to weak, maybe let's, yeah, yabona ngoku khona inkinga la. In addition to weak London forces that C6H14 has predominantly. Okay, now if that is the case, then we know that more energy is required to separate molecules than would be required for the alkane, let's just name, than for the alkane. Okay, so we know that this one has strong hydrogen bonds in addition to weak London forces that are predominant in the alkane. Therefore, more energy will be required to separate molecules in Q than would be for the alkane, and therefore Q will have a higher boiling point. I don't know why I keep writing boiling point than the alkane. I mean, there's a lot of things you can say. I mean, if you're comparing the strength of the intermolecular forces, that gives you perhaps 2 marks, I guess. And then if you mention energy, again 2 marks, comparing the two, which one will require more. And then 1 mark for that last little thingy there. Okay guys, so that's how the 5 marks are taken. So we're still on organic chemistry, so let's try to move quickly here. In the flow diagram below, 1, 2, 3, 4, and 5. Okay, so now we have to study these reactions and make sure we understand exactly how they go. All right, so we need to make sure we study them so well so that we can kill everything that is about them. Okay, let's just do it. Now in the, okay, we've read that statement. So we're starting here. Let's say we have a compound Y, which we are told is an alkene. Okay, and then it undergoes reaction 1 to compound X, which is an alkane. So when we convert an alkene to an alkane, what do? We are simply adding hydrogen gas. So this is basically a hydrogenation. Okay, hydrogenation. So reaction 1 is an addition reaction, which is hydrogenation. Okay, maybe let's not even waste our time writing there. Just hydrogenation. Okay, we know that that is hydrogenation. So what are the requirements for hydrogenation? What reaction conditions must we have? Okay, so basically we need alcohol as a solvent. Okay, so we need, because this thing is insoluble in water, so we have to dissolve it in alcohol. So we normally use ethanol. Okay, and then what do we do here? Then we need a catalyst. So usually we use nickel, platinum, or what is this one? Is it palladium? It's PD, something like that. Yeah. So that is those 3 usually that are written in your textbooks. Okay, so those are the things that we need for that reaction, and we said it is itself hydrogenation. Okay, so that's reaction 1 for us there. And then of course we move on. Reaction 2, we're changing our alkene into a 2-bromopropane. So this is a haloalkane. So basically this is hydrohalogenation. So we normally have a hydrogen combined with some compound X, which is the halogen. So this is the hydrohalogenation. So we're adding, it's an addition reaction as well. So what do we need for a hydrohalogenation? Okay, this is a pretty spontaneous reaction, but the condition that is important here is that there must be no H2O here, because if we end up with water, then water will start to give this one the OH minus ion to make an alcohol. Okay, so we don't want water, so this must not have water anywhere, or there can't be water in the environment. We can't use water as a solvent. Okay, not a problem. Otherwise, that is a pretty spontaneous reaction, so no issues there. And then reaction 3, we're converting our haloalkane back to an alkene. So this time we are going to eliminate something. So we're eliminating this hydrogen halide. So we are doing what we call a dehydrohalogenation. So this is a dehydrohalogenation. So we can just say minus HX there. So if we're taking it out, we are dehydrohalogenating it. So it's an elimination reaction. So what do we need for this? Remember, you are going to deal with the so-called Zaitsev's rule. Okay, so think of Zaitsev's rule here when you're doing that, and when we're adding, you think of Markovnikov's rule. Okay, so Markovnikov's rule, the reverse is Zaitsev's rule. Okay, so what conditions obviously would favor this kind of a reaction? Well, the conditions for a dehydrohalogenation is, first, we need a concentrated strong base. So the bases we use, they must contain the hydroxide. So it can be sodium hydroxide, potassium hydroxide, whatever. But the idea is that it must be a strong base that is concentrated, okay? Because we want to eliminate things, all right? And then what else do we need, guys? Of course, we still need alcohol as a solvent. All right, because this is insoluble. So we need to dissolve it in alcohol, which we normally use ethanol, okay? Then, what else do we need? We need to heat the reaction, okay? We heat the reaction, but we heat in a technique called reflux. Why should we do this? Because if we don't do this one in reflux, the problem is that the gas will sort of like form at the walls of the container and then go back into the reaction. So we don't want that. So whatever eliminate, we want it to not take part in the reaction again. So we do that in reflux. So these are some of the things you want to revise when you study these diagrams. But of course, don't take as long as I am taking, because I'm just trying to give you some ideas. So you just quickly look, and maybe identifying the type of reactions is the best you can do, and then you start answering. But at the back of your mind, have this in your arsenal. Okay, so reaction 4. What is the story about reaction 4? Reaction 4, basically we're taking this haloalkane and we're forming an alcohol. So this is an element. What is the substitution reaction? Okay, that is a substitution reaction. Now, what do we need for that substitution reaction? Of course, we call it a hydrolysis, okay, or hydration, whatever. It's hydrolysis. So here, what do we need? We need a dilute version of a strong base. That is, what is that? Potassium hydroxide, sodium hydroxide, but that one has to be dilute. Okay, so that is important. It's key. It has to be dilute, because if we put a concentrated one, we are simply going to cause a situation where we actually eliminate rather than add something, okay, or substitute something with something. All right, so what can we do? Why is it a substitution, by the way? Because this is already saturated. So for saturated compounds to form new ones by adding stuff into it, it has to undergo some sort of a substitution. Okay, so what else do we need, guys? Do we need more than what we have? Yeah. Of course, we need heat for this reaction to take place. All right, we need heat, and then of course alcohol as a solvent, because this is insoluble in water. Okay, Not a problem, guys. So we have essentially done a bit of our homework here. Now, what is that? Secondary alcohol. We are eliminating stuff to take it back to an alkene. So we are actually dehydrating it. So we call it a dehydration reaction. And then, of course, for a dehydration reaction, what do we need? For this one, to dehydrate an alcohol, we usually use a concentrated sulfuric acid. It has to be concentrated. Okay. So we use that as a dehydrating agent as well as, of course, a catalyst. All right. And then, of course, we need a little bit of heat. We will need heat here. So we will also need heat. Okay, enough, guys. I've wasted time here because I should be done answering here already. Yeah, but it's fine. So we are told here, name the type of addition reaction. So you can't say type and then say addition. It should be name the addition reaction represented by 1, because we want the name of the addition reaction. So we said this is hydrogenation. We are adding hydrogen. So this is hydrogenation. So 4.1. Oops. This is hydrogenation. 4.2. Now we're told to name the type. Again, I have a problem because they're telling you it's an addition reaction. So it should be name the addition reaction and not the word type. The word type is insignificant there. Reaction 2 there, it's hydrohalogenation. That's the name. So we can say hydrohalogenation. Okay, because we're adding a hydrogen halide. So 4.3 says, which of the above reaction uses platinum as a catalyst? You know, it's reaction 1, the hydrogenation. So do you see some of these things? It's reaction 1. They asked which type, which reaction. So you just name it reaction 1 like that. So 4.4 has some sub questions. So we have 4.4.1. So what does 4.4.1 want? It says now reactions 3 and 4. Okay. A base is required, as we have already stated here. So it says now write down one similar property of the bases used in both reactions. They are both strong bases. So these are very quick questions when you've done your bit of a revision. So these are strong bases or bases. 4.4.2. Now, what is the next question? It says describe fully how these bases used in both reactions are different. So how do they differ? So we will have to consider the first reaction. When they say fully there, they basically are trying to say you have to tell us what is the case in reaction 3, what is the case in reaction 4. So of course reaction 3 is what? We are eliminating. So we need a concentrated strong base. So we can say here the base is a concentrated, no, not a, concentrated strong base. But you don't have to add the strong because we already put it there. So this one we must use a dilute base. Okay, but the base is supposed to be strong, so yeah, that should be fine. Okay, and then here it says write down a balanced equation for reaction 2 using structural formulae. So reaction 2, so this alkene goes into that alkane. Okay, so we already saw that here there's a key that there is a propane. So this means it's a propene is going to form propane. Okay, so not a problem. So 4.5. So we have propane. So propane is like this. I mean, whether you put it here, it's still in the first carbon. So the double bond is like that. So you will have here hydrogens because they want structural formulae. So 1, 2, 3, 4. And then here there's going to be 3 hydrogens. And then of course we're adding hydrogen gas. So I mean here H2 is a diatomic gas, so it's fine. What are we going to form? We are going to form a propane. 1, 2, 3. So all right, so there it is. You don't have to really show the reaction conditions at this point. You just leave everything out. But you know there's going to be a catalyst, either platinum or nickel or palladium. And then you're going to need a bit of heat. All right. Okay. All right. Actually, no, we just need an alcohol and a catalyst, not necessarily heat, because it would be spontaneous. Okay, guys, that is cool. So the next question says, name the type of substitution. Again, this is a substitution reaction. So we want the name. So the word type is not necessary there. Come on, guys. What are you doing? You're repeating yourselves a lot here. This is not supposed to be there because it's confusing at the point. I mean, the type is substitution. So why are you putting it there? Putting it twice. Don't do it. We're not happy when you're trying to confuse us in a careless way. You have to confuse us in a very nice and logical way, a smart way, you know, scientific way. Don't try a very weak technique of confusing students, just for the fun of it, of course. Anyway, so we need the type that is 4. So we said here, this is going to be hydrolysis, okay? It's hydrolysis. So 4.6. It's hydrolysis. That's the name of the reaction right there. And then using molecular formulae, write down a balanced equation for the complete combustion. So remember, when they use the word complete, that is a key word. Because if it is incomplete, it produces carbon monoxide. But if it is complete, it produces carbon dioxide. So we're looking at compound X. So what is compound X? It's an alkane, which is a propane. So propane. So we have here 4.7. So we have propane 1, 2, 3. We set molecular formulae. So propane is C3H6 plus 2, which is H8, right? Plus oxygen. I always forget this is a diatomic gas. I just write a single oxygen, so please guard against that. So we're going to form carbon dioxide gas plus a water molecule. Now, what is that? So there's 3 carbons here, and then there's 8 hydrogens. So we put 4 there, but it doesn't look too nice here. So we're going to have 4H2O as a result. Now let's balance the oxygens. There's 4 oxygens plus 6, which is 10. So we can put a 5 in there. So this one is pretty easy. Not a big deal. So 4.8. What is 4.8 asking? So again, they're saying name the type of elimination. I mean, they say name the elimination reaction represented by 5. That word again is not necessary there. All right, reaction 5, we are basically taking an alcohol and losing water to form an alkene. So this is a dehydration reaction. So this is dehydration. reaction. Okay, not a problem. So that is fine. Now 4.9, a lot of questions. Compound Y is also produced. Compound Y is also produced from cracking reactions. I mean, we're taking long chain alkanes, we're breaking them into some alkenes and alkanes, but shorter chains so that we can bend them more efficiently. Okay, as shown. So we're taking a heptane basically, and this heptane, because there's 7 carbons there, then we have hydrogen gas. So you see guys, these guys, they like to confuse. There's already hydrogen gas out, and then of course there's twice of the compound K. Okay, and then we have compound Y, which we know already it's propane. Sorry, propene. Hayibo, itheni yakho loza e batla ho lwana. Re tla bolayana he ntate. Wane nna ha ke lwana ke a bolayana, ha ke bapale, ha ke tshameke. Anyway, so we already know that compound Y is an alkene, which is propene. Okay, so yeah, I'm losing time, guys. I don't know if I'll be able to finish this thing within the time that I should, but anyway, let's just try and go. Okay, so yeah, you see now I worked there and I'm supposed to work here. So now it says write down the IUPAC name of compound K. So there's 2 molecules of compound K. Remember, I already have 3 carbons here. So this one definitely will have to have 2 carbons. But this is also an alkene because there's already hydrogens that are sitting there alone. It was supposed to be a, what do you call? It was supposed to be an ethane, but because we already lost those hydrogens, so it's going to be an ethene. So that will be ethene. Ethene, not ethane. Let's write it nicely. I always move too quick sometimes for my own good. So it's going to be ethene, okay? But you're getting 3 marks because there's a lot of things you needed to consider. All right, not a problem. Not a problem. Not a problem. We are good. We are good. We are good. Okay, folks, that ends question 4. Yeah, it's a very boring question, I tell you. Now it's dark in here, guys, so I don't know if it was the best time to do my thingy here. Let me just try to sort out the light. Let's just pause and sort out the light. All right, guys, so I'm back. Just sorted my light bulb so that I can see my calculator when I do some calculations, because now we're going to start doing stuff like that. Okay, a group of learners use the reaction of excess. Once it's in excess, it's not a rate limiting reagent. So if you're going to determine things, you may not want to use the hydrochloric acid with magnesium powder to investigate one of the factors that influence a reaction rate. Okay, the balanced equation for the reaction is, magnesium solid, 2 molecules of hydrochloric acid in solution, forming our magnesium chloride salt, which is also soluble, plus hydrogen gas, which will bubble out. Now, they use hydrochloric acid of the same concentration and X grams of magnesium powder in each of the 2 experiments. So there's 2 experiments being conducted, and there's 2 conducted experiments. They use the same concentration of the excess hydrochloric acid, and they use the same mass of magnesium powder. So both experiments are carried out at 20 degrees Celsius. So you see the temperature is kept constant as well. so that it does not interfere with our reaction rate experiment here. Now the graph below shows curves 1 and 2 that were obtained for the two experiments respectively. Curve 1 is incomplete, so always take things that are highlighted so that you have less confusions. As you can see here, well, same mass. Remember, the end point should be the same, so meaning the volume. So this thing will slowly catch up. Oops, 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 oops. It will catch up there, all right? It will catch up there. So it's incomplete, but at the end of the day, if we used the same mass, remember magnesium is the rate limiting reagent, so it has to go completely into the reaction. So we will have to have the same amount. We must have the same amount at the end. So it just is a portion of it right here. Okay, not a problem. And then, of course, we have volume in centimeter cubed. Then we have time in seconds. Okay, not a problem. But if you're looking at these graphs, this one is much steeper than that. So meaning this one is faster than that. How can this one be fast when we're using the same concentration of acid, same mass of powder, meaning the same standard of division of magnesium? Well, temperature is the same, and you know what? These are aqueous solutions, so pressure will not really play a part that much here. So what could be the reason for this to occur? Well, a catalyst can lower the activation energy and make this one much faster than that. So meaning this one is most likely a catalyzed reaction. This is most likely catalyzed if we think of all the reaction rates that we have explored. This one is uncatalyzed. Okay. Anyway, define reaction rate in words. Easy marks. So 5.1. So when we define the reaction rate, it is defined as the change in the amount of reactants and or products per unit time. Okay, easy. Just use the more general one, which is amount, but it can be anything: concentration, number of moles, mass, volume, if gases are involved, all that. So that is easy marks. So let's keep going. Next question says, calculate the average rate of reaction, and it must be in centimeter cubed per second for experiment 2 for the time interval 30 to 60 seconds. So let's see at 30. Now let's look. This is 20. So the small block is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So it goes in twos, all right? So not a problem. So let's see there at 30. Reaction 2 is at 64. All right. So it's sitting at 2, 4 right there. Okay. And then at 60, it is sitting at 104. Okay, it's 104 because that is sitting over there. All right, not a problem. So that is what we needed to find out. Okay, so the next is, the next step is easy. So the reaction rate is going to be the change in the volume over the change in time, because we said an amount, it can be anything. So we have volume there of hydrogen gas. So this is effectively 104 minus 64 divided by 60 minus 30. So let's do that. Now I have this lovely bracket here, 104 minus 64 close it, 60 minus 30, which is just 30. It is just 30. Ngeke yaqoka. Iqoka qoki tyhini funa ngiqhela kabi. Getting 4 over 3, which is 1,33. Always can choose 2 decimal places or even more. So this is going to be centimeter cubed per second. Okay, not a problem. We have sorted that one easily. Now the next question, it says, which one of the experiments, 1 or 2, took place at a slower rate? Give a reason by referring to the graph. So the reason must be on the graph, because we said, well, most likely catalyzed, but they don't want that reason. So look, the only way we know this one is slower because the gradient of the curve is much gentler than the gradient of so we can say reaction 1, 5.3. So it is reaction 1. It is reaction 1. Why? It has a less steep gradient. Okay, not a problem. So we don't want to say too many things there. We sort it out like that. Now it says write down the factor responsible for the difference in the rate of reactions. So, well, probably a catalyst here. So 5.4, we can say a catalyst is likely used in 2. Okay, not a problem. Maybe let's write it properly. A catalyst is likely used, okay, in 2. Okay, let me just take this call quickly. Okay guys, I'm back. I've taken the call, so let's just continue. So a catalyst is likely used in 2. Okay, not a problem. And then let's keep moving, guys. Using the collision theory, fully explain how the factor in question 5.4 affects the rate of the reaction. So this is one of those questions which are always there. So you must get used to answering them. So we can say a catalyst lowers the activation energy required for effective collisions. Okay, effective collisions are basically the reaction, okay? For effective collisions to take place, okay? Number 1. And then if that is done, then it means more molecules of reactants will have enough energy will have more molecules, more reactant molecules, or more molecules of reactants will have enough kinetic energy. Let's just say we'll have enough kinetic energy and form more regular effective collisions per unit time, okay? And that will increase the reaction rate. Again, guys, don't focus too much on my writing. It's ugly, I know it, but the idea here is to just give you a little bit of a simulation of doing that exam. Let's just see if we will be able to do it in time. Okay, so that is basically how we can explain this using the collision theory. So let's deal with the big one here. Big one quickly says, calculate the mass of magnesium powder remaining. So what do we want? The mass that is remaining in the container at what time? At 150 seconds for experiment 1. Okay, now it says take the molar gas volume as 24,040 centimeter cubed per mole, okay, at 20 degrees Celsius, which is the temperature at which these reactions are taking place. But let's look here. This one at 150, if you look at it, it's sitting at a volume of 102. Okay, the volume there is 102, okay, for reaction 1. But, well, why do we know that this is incomplete? It's because it hasn't reached that plateau. Now, what is the plateau for reaction 2? It's 120. So meaning at the end it should be 120, but it's there. So we will use 120 as our final. And then we subtract this one. It will give us the volume that is missing. That's what we want. That's the remaining volume. Okay, not a problem. So how do we start a question like this then? Well, we're going to first say, for us to calculate the mass of magnesium, we will need to find the number of moles. Okay, we need the number of moles, but number of moles of what? We need the number of moles of magnesium that reacted versus the number of moles that have not reacted. So the number of moles that reacted, we know that when it reacts completely, it's going to be that. And then when it doesn't react completely, it's going to be whatever we find here. Then the difference is what remains. Great. So let's say the number of moles that react. So we can just say for 2, it gives us the number of moles of magnesium in total is going to be equal to essentially the number of moles of hydrogen gas produced, right? Okay. Number of moles of hydrogen gas produced in a complete reaction, of course, in a complete reaction. Now, this is equal to, now we know that the molar gas volume is going to be volume over molar gas volume. All right, let's deal with this one. So the volume there is 120. Divide by the molar gas volume here. They gave us 24,040 centimeter cubed. So this is in centimeter cubed, so per mole. So we don't have to really do too much there. So we have 120 divided by 24,040 centimeter cubed. So here I'm getting 4,99 times 10 to the minus 3 moles. Okay, so that is the total number of moles of our magnesium. That is the total. Maybe let's just say total, because it's better to show that this is the total. But now in reaction 1, it's an incomplete one. So now for reaction 1, what we have here, the number of moles of magnesium. So now this is not the total, okay? That is used. I don't know what we're going to say. Anyway, we're going to deal with this one this way. It's going to be equal to the number of moles of hydrogen gas produced in 1, okay, which is an incomplete reaction. So this is going to be V over Vm. let's just go about it this way. So that one was 102, right? Did I find it to be 102? Yeah, this is 102. Is it 102? What did they say? At what time? 150, yes. At 150, this one is definitely 102. Okay. So it's going to be 102 divided by 24,040. So let's see, 102 divided by 24,040 is what? So I'm getting 4,24 times 10 to the minus 3 moles. So we can say, therefore, the number of moles of magnesium remaining is going to be equal to the total there, which is 4,99 times 10 to the minus 3 minus this 4,24 times 10 to the minus 3. Alright, so we have 4,99 minus 4, minus to the exponent minus 3 minus 4,24 exp minus 3. So I'm getting here 7,5 times 10 to the minus 4 moles. Now that we know, we can say therefore the mass of Mg that remains is going to be equal to the number of moles, which is 7,5 times 10 to the minus 4, divided by the molar mass of magnesium, which is 24, right? So we just divide that by 24. Wait, the mass, we basically multiply, we don't divide. Okay, problems. So we multiply by the molar mass, which is 24. Okay, multiply by 24. So what are we getting? When? Okay, wait. What is that? This is 7,5. 7,5 xp minus 4 times 24, right? Yeah, I'm getting 0,018 grams. Okay, so I hope my calculation is correct. Otherwise, there is going to be some sort of tears if the calculation is not quite correct. But let's just double check here. It says, yeah, the remaining in the container. So remember, when you want to not miss anything, you look for the number of moles. So I think our calculation is fine. Yeah, that is it, guys. So we are sorted. So this is the answer there. So it is an 8-mark question, so it tells you that you have a lot of things to do. So first, you're getting that number of moles, meaning the total number of moles of magnesium that we have because we used a certain mass, and then finding this number of moles in that experiment 1 is important, and then to get the difference is important. And then I hope I'm not making a meal here. Yeah, 1 mole of hydrogen gas produces 1 mole of magnesium. So 1 mole of magnesium gives us 1 mole of hydrogen gas. So there's no issues here. So 1:1. I don't think there is any issues. Therefore, we leave it here. But forward, I think we are good. Good. Is good is nice. Is nice is good. Okay. Yo, I'm tired now of bending. Ek is moeg, man. Ek is nou moeg so. Ek is nou moeg. Now we just keep going, guys. There's nothing left to do. There is nothing left to do. Yeah, I think our question is sorted. Magnesium, yeah, that is it. Let me just double check my periodic table. Hey, one in Bilaela, Why am I not quite settled? Let me just get my periodic table. Yeah, magnesium is 24. So it's 24. So yes, Bafueto, I think our calculations are correct. But make sure you have the method, because that is what matters more than the rest. So let's quickly run through question 6. Now question 6 says, consider the reaction represented by the balanced equation, which is, okay, below. It's already balanced, okay? Now, once you see this, you know that we are doing chemical equilibrium, okay? So we have 4 molecules of hydrogen chloride gas plus oxygen to form 2 molecules of water and chlorine gas. Now, initially, what happened initially? We put 1 mole of HCl. Okay. And then an unknown mass of oxygen. Okay. We don't know the mass of oxygen gas that we put in there. Now we're mixed in a sealed container, so the volume is 5 decimeter cubed, and then the temperature is 600 degrees Celsius. Okay, equilibrium was established, and 28.4 grams of chlorine gas was present in the container. So this is at equilibrium. So we have ourselves a bit of a dance here. So 6.1, define the term equilibrium, which is easy. So we know that equilibrium is defined as a reversible chemical reaction, because I said chemical equilibrium, right? Not just equilibrium, but chemical equilibrium. So it's a it's a reversible chemical reaction where the forward reaction is equal to the reverse reaction. Okay, so chemical equilibrium is basically a reversible chemical reaction where the forward reaction is equal to the reverse reaction. That is what is important. Or it's a chemical reaction where the concentration of the reactants and those of the products remain constant. So those are some of the things you can say to survive that question. Again, it's a simple one. No need to say too much. Give a reason why the reaction above is homogeneous. So it is homogeneous because all the reactants and the products are of the same state of division or same phase. They are in the gaseous phase. So we can just say here 6.2, can say all reactants and products are in the same phase, which is the gaseous phase. Okay, they're in the same phase, so basically that's what matters. Okay, next one. So the big one, okay. Now calculate the initial mass of oxygen if the equilibrium constant is 800. Okay, so they're giving us Kc. That Kc is 800. Okay, so no issues. We're going to deal with it just right. Okay guys, let's just get to this one. But the manner in which I do this question is to write this equation again. So 6.3, let's write the equation again. So this is 4HCl why do I even bother? Yeah, I don't want to have problems. Plus oxygen gas, it gives us what? 2H2O gas plus what? The last one is 2Cl2. Yes, okay. So now what I normally do here, I go the initial number of moles, okay? Nice one. And then I can say used and or produced number of moles is that one, and then we know that equilibrium number of moles again, and then we want the equilibrium concentration. Of course, that is in mole per decimeter cubed. So initially, what did we put? We put 1 mole of hydrogen chloride. So here we have 1. Therefore, we're going to have X amount because we don't know how much of oxygen we put in there. And then initially, there shouldn't be anything for these two. But now we found out that at equilibrium, we found out that there was 28.4 grams of chlorine gas. So the number of moles at equilibrium for the chlorine gas is going to be basically 28.40 divided by, remember chlorine gas, when you have a subscript, don't mind the coefficient. What matters is a subscript. It's a diatomic gas, okay? So if it is a diatomic gas, what does that mean? It means we will double the molar mass for a single chlorine atom. So this is going to be 2 into 35.5. What is that? So we have 28.40 divided by, is that true though? Yeah, well, can't make mistakes now. Yeah, 28.40. Then divide by 2 into 35.5. Is it 35.5 or 36.5? Okay, let's check the periodic table there. So it's 35.5. Okay. So I'm getting here 0.4. So meaning at equilibrium we have 0.4 moles. That means we must have formed exactly 0.4. Then now 2 is to 2 for this 2. So also this one is going to be 0.4. Okay. Then that one is 4 times that. So it's basically double that. So we double that 0.4. So when you double it, we get a 0.8 here. That is what we used. So we're using the ratios here. And then here is 2 is to 1. So we have the 0.4. Divide by 2. It gives us a 0.2. Okay. So that is what we used. So this ratio is very important. And then of course, this one means we formed, at equilibrium, we're going to have the same here. And then, what is that? It's going to be x minus 0.2. That is going to be 1 minus 0.8, which is basically 0.2. Okay, that's all right. And then now we want the equilibrium concentrations. It is going to be basically 0.2 divided by 5. We know the container is it's 5 decimeter cubed. And then here's going to be x minus 0.2 divided by 5. And then we're going to have here 0.4 divided by 5. 0.4 divided by 5. And then what would be that answer there? Divide by 5. I'm getting 0.04 mole per decimeter cubed. And then this one, you leave it as it is. Okay, the power came back, which is good. So this one is basically going to remain as x divided by x minus 0.2 divided by 5. What is that? 0.4 divided by 5. This is 0.08 mole per decimeter cubed. 0.08 mole per decimeter cubed. And then we deal with this Kc story now. We're going to say find Kc is equal to the concentration of our reactants, which we can use water there, 2 moles of it. So it's going to be H2O squared multiplied by the chlorine gas. Also it's squared because there was a coefficient of 2 there, okay? And then this is over the concentrations of the reactants. So we have HCl here, which is going to be raised to the exponent 4, multiplied by the concentration of oxygen, which has no coefficient, therefore it's not raised to any exponent. And then we substitute. So they told us that 800 is equal to, now we found the concentration is 0.08 squared into 0.08 squared, divide by, this one is 0.04 to the exponent 4, multiplied by x minus 0.2 over 5. Okay, now guys, you need to be very smart about it. If you have fractions, we do gymnastics here, mathematical gymnastics even. So we want to get x to be isolated. So eventually, I'm not gonna really bother now. You already understand maths. If you don't, I'm sorry guys. Yay. So this multiplied there, this whole thing basically multiplied there, and then we divide by it. We're going to first divide by this here, then we will multiply 5 into whatever that fraction becomes, then we subtract 2 from the whole thing. So this is going to be 5, okay, into 0. Come on, don't be showing me messages here. This is 0.08 squared multiplied by 0.08 squared. Okay, all of that we divide by this one, 0.04 to the exponent 4, and then we will then add 0.2 at the end. So I mean, you already know, if you put this apart, you just arrange it so that you can have your answer, but please be very careful. Mistakes do happen here easily. 0.08 squared into 0.08 squared, okay, and then we divide that by 0.04 raised to the exponent 4, and then we close that, and then we add 0.2. What do we get? Okay, that can't be true. Something is not making any sense right now. 5 into, let's just say 0.08 squared times 0.08 squared, divide by 0.04 raised to the exponent 4. Now it's starting to lie. Hey, it's got lontina. Ibatlauri. Yeah, when? Ho. Hi. khona into engenzi sense ke manje. I don't understand. Huh? Hayi wena. Akukho sense ke ngoku apha. Oh, I forgot 800. Yeah, when? You see now my gymnastics. Hey, we're not complete flops. And if you do such a thing when you do gymnastics, you're gonna land on your head and break your neck. That's exactly what I just did. I landed on my head and my neck is broken now. Hey, wena man. O batla ho mpolaya wena man. Ska tlo mpolaya mona. Hey. Ke magetse gore ha etse sense into wena. I'm getting 80, something. How can that be? It's not possible, eh? Okay, now that I know my number of moles. Remember, this is moles. Remember, that was the number of moles, which was X right there. So, what are we calculating here? We are calculating... what we are trying to calculate here is the initial mass of oxygen. So basically the mass of oxygen is going to be, again, the number of moles, which is 0.3, multiplied by the molar mass, which is 16 by 2, which is 32. So this is times 32. I'm getting a 9.6 grams. Okay, that should be the answer. All right, guys. Yeah, hey, these questions can do a number on you if you're not careful. So I made a mistake here, which is, you know what, a normal thing. So let's not even try to mark ourselves at this point. Time is not on our side. All right. So we've sorted that. So let's do 6.5 quickly. Now it says the volume of a container is now decreased to 2.50 decimeter cubed. Okay, so if we decrease the volume, what are we effectively doing? We're increasing the pressure. Okay, while the temperature is kept constant. Okay, now it says how will each of the following be affected? Choose from increases, decreases, remains the same. What is the value of Kc? Remember, value of Kc for the same temperature remains constant. So 6.5.1, we know that it remains the same. 6.5.2. Now, the mass of chlorine gas in the container. Now, let's look at our equation. If we look at our equation, there's how many number of moles on the left-hand side? 4 plus 1, that's 5. Here we only have 4. So if we increase the pressure, we will favor the reaction that increases. That decreases the number of molecules. So it will favor the forward reaction. So this will increase. So we are going to say it increases. Okay, that is Le Chatelier's principle. Okay. Hey, there's a lot of questions here. But what happened? There are some questions I did not answer here. Yeah, man. Now I can see there's a crime I committed here. I have committed a crime. So 6.4 I did not answer. Yeah. So let's answer 6.4 first. Okay, 6.4 says basically state Le Chatelier's principle. All right, not a problem. So what does Mr. Le Chatelier, I don't even remember how it's written, Le Chatelier's principle. So Le Chatelier's principle states that, okay? Yeah. Hey, ixesha liyasidla bafowethu, angazi ukuthi sokwenze njani ke uma sekunjena ke, because hey wena ixesha alimanga nathi, but ke masizameni bafowethu sesiseduze. It says when the equilibrium okay, in a closed system, okay, is disturbed, okay, the system will reinstate, okay, that is reinstate a new equilibrium okay, by favoring the reaction that opposes that disturbance. Okay, I'm sorry guys, I ran out of space there, so that's not a problem. So that is it. That is Le Chatelier's principle. Of course, there's lots of ways you can state it, but please make sure you carry on that there will be a new equilibrium by opposing a reaction that, by opposing the reaction that caused a disturbance in the first place. Okay, not a problem. And of course, mention a closed system. So yeah, that is the crime that I committed right there. Otherwise, everything else is not really done any crime too. All right, so that is it, guys. I don't know why I left so much space. Okay, there is 6.6 here as well. Sure. All right, 6.6. I don't know what I was doing here. Whether I was smoking ganja or what, but I don't smoke ganja, guys. Don't think I'm smoking ganja. I don't. Now it says explain the answer to question. Okay, maybe let's do something smart here before we look like hooligans. I don't know why I didn't do this one properly. Yeah, hey, ixesha kodwa lona selingikhabe ebusweni bafowethu, angisazi nami ukuthi sengenza ntoni manje, sekwenzeka izinto engingazithandi. All right, let's just do this bafowethu just for a second here. Just a second. Okay, let's just do something here. Hayi wena suphapha, theni ngathi uyaphapha nje, phaphelani, hayibo. Okay, so 6.6, let's just do it here. Okay, let's just do it here. Left a lot of space here for this question. Now explain the answer to question 6.5.2 by referring to Le Chatelier's principle. Okay, now we know that if we're forming this one, we can just say decreasing the volume of the system essentially increases the pressure of the system. Okay, now according to Le Chatelier, so according to Le Chatelier's principle, according to Le Chatelier, okay, Le Chatelier's principle, The reaction that decreases the pressure is favored. This is the forward reaction. Okay, so according to Le Chatelier, the reaction that decreases the pressure is favored, which is the forward reaction. Therefore, more Cl2 gas will form. Nice, easy, né? Not a big deal. So we've sorted that question. So 6.7. We have to answer the question. It says now, the temperature of the container is now increased, okay? When the equilibrium is reestablished, the value of Kc is 450. So remember, at the initial it was 800. Now it dropped to 450. Now 6.7.1 says, is the heat of the forward reaction, remember forward reaction, is it positive or negative? The answer is negative. Why do I know this? Remember, if we dropped this one, if we increased the temperature, we always favor the endothermic reaction. So the endothermic reaction is the reverse reaction here, because we can see the Kc value decreases, meaning we increased the concentrations of the reactants by dropping the concentrations of the products. Okay, not a problem. And then, of course, the next question says, explain the answer to question 6.7 by referring to Le Chatelier's principle. All right, not a problem. So we can say here, increasing the temperature of the system will, according to Le Chatelier's principle, will according to Le Chatelier's principle favor the reverse reaction, which is endothermic, okay, or will favor the endothermic reaction. Now we can say more reactants will form while products decrease. Okay, this will result in a smaller Kc value than initial, or than the initial one. All right, so I've tried again. So please guys, make sure whatever you say makes sense. So if you increase the temperature, favor the endothermic reaction. Now the reverse reaction is the endothermic, because we can see that the reactants formed while the products decreased, and this essentially decreased our Kc value. Done. So we're going to question 7, another situation. Let's try and kill this one quickly, because if we can kill this one quickly, we will then quickly run through our redox reactions, which is quite easy. Now consider the following reaction: hydrogen sulfate, or you can say sulfuric acid in solution, plus molecules of water. Now remember, this is basically adding acid onto water. You don't add water onto the acid. So this is basically diluting our sulfuric acid, essentially. And then it will dissociate into its ions. Of course, first we get this hydrogen sulfate ion plus the oxonium ion. Now it says define an ampholyte. Quickly, guys, what is an ampholyte? 7.1.1. So an ampholyte is a substance that can react as both an acid and a base, okay, depending on whom it is reacting with. So it is a substance that can react as both an acid and a base. So that is the essence of what an ampholyte is, and we know water is an ampholyte. Okay, now 7.1.2 says apart from H2O, which substance in the above equation acts as an ampholyte? And then we know that it is the water and it is the hydrogen sulfate ion, because this one can protolyze water to form yet another oxonium ion and leave out the sulfate ion alone. So we can go on and say 7.1.2, it is the hydrogen sulfate ion. Okay, not a problem. Not a problem. That is a 1 mark. So now we're getting to some situations. 7.2 says a solution of hydrochloric acid has a concentration of 0.1 mole per decimeter cubed. Calculate the pH. Straightforward question here. Now, what is this, by the way? This is HCl. Okay. So this is 7.2. So 7.2.1, we know that, well, HCl in water will form just one molecule of the oxonium ion plus the Cl minus ion. Okay, so now we essentially know that the concentration of the hydrochloric acid, because it's a strong acid, it dissociates completely. It will be exactly the same concentration of the oxonium ions. So we can say now we understand that the pH is going to be minus the log of the concentration of the oxonium ion, which will be effectively minus log of exactly the concentration of the acid, which is 0.1. This is basically a pH of 1. pH does not have a unit. Okay, done. So this is a standard 3-mark question. Formula, substitution, answer. No question about it. Okay, now we're getting to some serious problems. So 7.2.2 says now a flask contains 200 centimeter cubed of an aqueous solution of sodium hydroxide. So sodium hydroxide is contained in a 200 centimeter cubed and of a concentration of 0.1 mole per decimeter cubed. So that is the essence of what is contained in that 200 centimeter cubed of a flask. Now it says to this flask 50 centimeter cubed of an aqueous solution of barium hydroxide of an unknown concentration is added, giving a total volume. So what is the total volume there? Okay, the total volume is 250 centimeters cubed. So this is going to be more like the Eastern Cape June question that really destroys your mind a bit. Okay, all right, okay, so we can handle that, guys. Not a problem. Now you see, once this starts singing, you start getting lost. I know. In a titration, now we're doing a titration this time around. We're doing a titrase. So now 20 centimeter cubed of this mixture Now remember, what mixture of the 250 centimeter cubed? Now we're taking only 20 centimeter cubed and we neutralize it completely, okay, with what? 30 centimeter cubed of a hydrochloric acid solution of that concentration we calculated above. Now we know that, well, these other ions, barium and the other stuff, sodiums, are basically going to be spectator ions. So the reaction is between the acid, which is the oxonium ion, and the hydroxide ion to form water. Now this question is asking, what is the pH of the solution when the end point, or we call it the equivalence point, of the titration is reached? Well, water, it is going to be the pH of water. All right, so what is the pH of water? Is definitely equal to 7. So it's going to be equal to 7. No problems, no questions, nothing. Now 7.2.3 says calculate the number of moles of the hydroxide ions present in the 20 centimeter cubed of the mixture of sodium hydroxide and barium hydroxide solutions. But remember, we took that and reacted it completely with the acid, so we can use that acid-base reaction to calculate the number of moles of says what is the number of moles of the hydroxide ions, which is essentially those that come from both the barium as well as the sodium. Okay, not a problem, we can do it. I mean, it's a 4-mark question. It's an acid-base reaction. So 7.2.3, we know that we can use our acid-base reactions. Concentration of acid, volume of acid, over concentration of base, volume of base, is going to be equal to the number of moles of acid over number of moles of base. This implies, what is the concentration of acid? Is 0.1 multiplied by, remember now, what was the volume of acid? It's 30 centimeter cubed. So now we convert that to decimeter cubed. So 30 divided by 1000 is 0.03. So this is going to be 0.03 over, now concentration of the base, we don't know. So this is going to be the concentration of the base. Wait. We know that, we don't know the concentration of the base here. When? So we need the concentration of the base here, basically, which is going to be Cb multiplied by, what was the volume? It was 20 centimeter cubed. So this is now 0.02. This is equal to 1:1, because I mean, in this equation we have 1:1. Not a problem. Therefore the concentration of the base is going to be 0.1 multiplied by 0.03 divided by 0.02. This is when you cross multiply there and divide. So let's do it. 0.1 multiplied by 0.03 divided by 0.02 is basically 0.15 mole per decimeter cubed. Okay, so that's fine. But that's not what we want. We want the number of moles of the base. We can say therefore the number of moles of the hydroxide ion is going to be, if we want the number of moles, is going to multiply the concentration, which is 0.15, multiplied by the volume of the base, which is 0.02, right? So we wanted the number of moles. So 0.15 multiplied by 0.02, I am getting 0,003 moles. All right. So that is what the question wants, okay? It wants the number of moles present in that 20 decimeter cubed. So that is it. So you can see 4 marks, 2 steps. Unnecessary. Okay, let's keep going. 7.2.4 is asking, it's a big boy. You win. Calculate the initial concentration of the barium hydroxide. Calculate the initial. So we want the initial concentration of the barium hydroxide, meaning we want this 50 centimeter cubed of barium hydroxide. So yeah, it's going to be a back and forth flip-flop here. Gymnastics are necessary here. If you can't do it, I'm sorry guys, if you're not fit, you're going to break your necks and stuff here. Okay, that was added to the sodium hydroxide solution. So what do we need, guys? Well, we need to find out how many number of moles of the hydroxide ions were present in that 200 centimeter cubed. Right. Yeah. Hey, it's a very technical question. Wait a minute. So if we can have the number of moles of the hydroxide ions, then we will calculate the total number of hydroxide ions, because remember, some of them came from the barium hydroxide, some of them came from the sodium hydroxide. So we can find the total first, then find that, because if we take the total and subtract there, it will give us the number of moles that were here. And then of course, from this number of moles, we know the volume. Then we can find actually the answer. Yeah, we can find the answer. Yeah, it's going to be a very tough question. So let's first find the total number of moles of sodium hydroxide in the 250 centimeter cubed. Because now we have to go back. But now what do we know, guys? We found out that the concentration, because we took a portion of that 200 centimeter cubed, we took just 20, but remember the concentration will be the same. We just took a smaller volume, that's all. So let's find out the total number of moles in this whole experiment that we had. So we can just say the number of moles, the total N tot of this hydroxide ion. We just want to use the hydroxide ion at this point. That were present here is going to be the concentration, which is 0,15 that we found, multiplied by the volume, which is 250 centimeters cubed. So this is 0,25. Ne? Divide by 8 grand. Yeah, this is 0, look at my minus. It looks like an x multiplied by 0,25. Okay? So we multiply this by 0,15. Alright, so this one gives us a 0,0375 moles. Okay, mole. Let's just say mole. Alright, so that is the total number of moles of the sodium hydroxide that was present. Now, let's think about it. That is the first step. But the next step is to say, how many moles of the sodium hydroxide were present? Because now that was 200 centimeter cubed. So we want to find out. So we have ourselves here. We can simply say, look, it's easy. We can now try to complex this equation because I'm getting tired. So we can say this implies that the number of moles of the OH minus in the BA, okay, maybe let's say in barium hydroxide, okay, is going to be equal to the total, which is 0,0375 minus the number of moles in, okay, maybe let's write a formula so that it makes a bit of sense. It's going to be the number of moles of the hydroxide ion total minus the number of moles of the sodium hydroxide ion in sodium hydroxide. Okay, we've written a nice formula here, so which is going to be the total is 0.0375 minus this one is going to be basically 0.1 multiplied by 0.02. Is it 0.02? No, it's 0.2. Now, where do I get the 0.2? Remember that was initially 200 centimeter cubed, so you divide that by 1000, you get 0.2, and then that you multiply by 0.1, which was its concentration. So let's see what is the number of sodium, of the hydroxide ion. So we just subtract here is 0.1 times 0.2. Yo, washu and that this is 0.0175 moles. Okay, so this is the number of moles of the hydroxide ions in the barium hydroxide. Okay, now we are almost there. How visually the end. So you see, this is a complicated calculation. It's gonna mess you up a little bit, but just hang on. Now we know that, okay, if we know the number of moles, what do we want? We want the initial concentration of barium hydroxide as a compound. We want that as a compound. But let's look here. If we dissolve barium hydroxide, we can say now the solution of Ba hydroxide, right, is such that is represented by this equation. Is going to be BaOH2 into water. Of course, it gives us a dissociation of barium 2 plus. Okay, it's going to be barium 2 plus the 2OH minus ions. Okay, so it will dissociate into 2. So now we know that this concentration is literally 2 moles. Yo, ya negafiwa la bafowethu. Hayi bebeyishayile ke leni intambo. They literally gave you a rope to hang yourself here. And this is a tough rope. It doesn't spare your life at all. You need a miracle to survive here and a very strong mind. Okay, not a problem, guys. Let's have a look here and see what is the story. The story that we have is so. We can therefore tell that therefore the number of moles of the barium is basically half the number of moles of the sodium hydroxide. Of the hydroxide ions, because this is 1 is to 2 or 2 is to 1. Okay, which we know that is going to be a half. Why is my 2 hungry? Now what did we have? There's 0.0175. Okay, because that is the number of moles of the hydroxide that were present in this barium. We calculated it above. Okay, let's see what is that. Yo, then we divide this one by 2. Then what do we have here? We have 8.75 times 10 to the minus 3 moles. So that is the number of moles of our original barium hydroxide. We can now conclude that the concentration, because that's the question here. So we can say therefore the initial concentration of BaOH2 is going to be equal to the number of moles, which is which is that 8.75 times 10 to the minus 3 moles, divided by the initial volume, which is finally 50 centimeter cubed. So 50 centimeter cubed is basically 0.05 decimeter cubed. Yo, eventually. Yeah, monna ra fihla. Yes, that's 0.175 mole per decimeter cubed. Yeah, when. Yeah. I feel like this one is more of an 8-mark question than the KC question there. But yeah, I'm not even going to try, guys, and show you where those marks are. This was meant to kill you, and if you died, you rightfully died, because this is a killer. But if you didn't die, you are definitely not the dying type, okay? You don't respond very well to threats. You are a Mboro type of a person. Mboro liwen. Okay, question 8. Let's run through question 8, guys, because we have done what hurts a lot quickly. Let's see if we can save a bit of time. Again, you can see that I'm only losing time because so if you talk less and you don't have to explain a lot, you just get to the thing yourself, you'll probably have a lot of time left at the end of this. This is usually the easy part. Sometimes it's better to start with this question 8 and 9 because those ones are straightforward. You chow those quickly, you get them out of the way, and then you do the MCQs. Or you can start with the MCQs just to warm up, because sometimes those can give you an understanding of how those questions that are coming in the long sections are going to look like. So you chow MCQs, and then you chow these next, and then you go and chow the reaction rates. It's quite easy to deal. Organic chemistry is just too intensive, but it's easy to answer, so you don't want to start there. You can answer organic chemistry part even under pressure. That one is long, but you can answer it even if you're in a hurry. There's just a few questions that can mess with you. And then you come to these big boys and girls. They will take you down a little bit. You wrestle them. Once you're done, then you can go and quickly chase organic chemistry. Even if you lose marks in organic chemistry, there's usually 1 mark or 2 that you may lose. Not as much as you would with these long questions here. Anyway, I started my talking. Now the equation below represents a reaction that takes place under standard conditions in an electrochemical cell. Now the electrochemical cell here is a non-specific term here, because we know that an electrochemical cell can be either be the electrolytic or the galvanic. Now we know here that, well, it's iron 2 plus some element we don't know. Ions of another element that we don't know, going to iron 3 plus. So do you see the oxidation number is increasing? So we are undergoing oxidation for the ion, and then there was a plus charge, now it's gone, so we are decreasing the oxidation number, so that is a reduction. So this is a redox reaction, which is still can either be electrolytic or galvanic. Now let's see. X is an unknown metal. Fine. The initial EMF is plus. Now this situation here, once it is positive, then we know this is a spontaneous reaction. Therefore, we are talking about a galvanic cell. A little bit of a quick revision will help you a bit, because they didn't tell you what cell you have. So you may have a question that asks you about it. Okay. Now, we don't want to waste time. Write down the type of there it is. The type of the electrochemical cell in which the reaction takes place. Now we can say this is a galvanic cell. Why? Because its E cell potential is positive. Now state 2 standard conditions for the above cell. Okay, we know that the temperature must be 25 degrees Celsius or 298 kelvins, and then the concentration should be 1 mole per decimeter cubed. Okay, great stuff. And then pressure is 1 atmospheric pressure, so any 2 of the 3 will work for you. Okay, is the above reaction spontaneous or non-spontaneous? The answer is it is spontaneous. Give a reason for your answer. we can say the the electrode potential of the cell is positive. Okay, that's it. No need to say too many things. Write down the cell notation for the above. So they want a cell notation. Okay, now let's think about it. Look. Okay, there's something I missed here. The cell uses platinum, but in any case, even if you missed that, you would know that if you have ions or gases, you need an electrode. You need a metal that is inert, which is not going to take part in that reaction. So you can use either carbon or things like platinum. So now the E cell notation, we're going to have platinum solid for the anode with the 2+ ions of that one, which will go to Fe 3+. Then we get a salt bridge. Then we have this this element, which is +1+ going to X solid. So that is effectively that. They didn't dictate that, say what are these in but this is aqueous solution. But maybe we can write it down and say this is AQ, this is still AQ, and that is AQ, and that is solid. So the state of division is fine, but that is essentially how that E cell looks. Okay, not a problem, not a problem. Now let's deal with this one. It says write down. Remember when they say write down, no explanations. The half reaction that takes place at the cathode in the above reaction. Of course, the cathode is undergoing reduction, so we are expecting to see a decrease in oxidation number. So if it is just 1+ going to a solid, it must have taken just 1 electron. All right, and then it goes to just X solid. Okay, maybe this is AQ if you want. Not a problem. So I'm just squeezing things. Now this is when they tell you you have 5 minutes to go, because we have exhausted our time. They'll say 5 minutes to the end, and then you're like, okay, let me try and finish this question. I'm almost at the end. Identify metal X with an aid of a calculation. So this is easy. E cell is going to be E of the oxidizing agent minus the electrode potential of the reducing agent. Okay, you can say reduction, oxidation. These ones, they just confuse you a little bit. So this implies, what is that? We got what? 0.03 volts. So this is 0.03. This one is just the E cell of X, because we don't know what that is, minus that one of ion. So if we consult our standard electrode potentials there, or we call them reduction potentials, okay, because these are placed in a way that would be signifying reduction. That's why it's called reduction potentials as well. So what is that? Let's look for the ion. Where's the ion one? There is that one. It's not this one. We want the one that starts with a 2+ and then it goes to a 3+. So there's plenty of them ions. So where is our friend? Ya wena, Scotland-tin. Uyipatetseng. Akinanako man. Kiyona yena. There's our friend. Okay. So we know that the oxidation of reaction is going that way. So what is the electrode potential? Is plus 0.77. All right. Okay, let's go back to our thing. Now this is minus. This is minus 0.77. Then when we transpose that to that side, we can say therefore the electrode potential of X is going to be equal to 0.03 plus 0.77. Now when you add these two, you're getting 0.7 plus 3 is 10. You add 1, it's going to be 80 volts. Hey, now we go back again. This back and forth is killing me. Which one is a +8? Okay, we need to identify which one. Now we see that this is either the nitrate ion or the silver one. So we know that that one goes into solid. So remember, nitrate ion doesn't go into any solid, so it can't be this one. So it can't be the nitrate, but it has to be silver because we see that it accepts exactly one electron even. So that must be silver. So yo. Now we can say therefore X is silver. Or you can write Ag. Done. Alright guys, I'm not even going to attempt to show you where the marks are. You know the procedure by now, so I don't have to explain it to you. So that is it. So you see, you can really, in those 5 minutes, you can answer even one more question because I've done it in 5 minutes. So let's just take the extra one. Extra 5 minutes where now they're really pushing you and you're like, no, I'm trying to hold on. Okay, the simplified diagram below shows an electrolytic cell. Now they're telling us used to electroplate iron spoons with copper. Okay, so what are we using? We want to make them look like copper. We want to make them look brown. Okay, so we have a DC power, and then of course if these are the spoons, then they are connected to the negative terminal, whereas that one is connected to the positive terminal. Why this one? It must be the cathode, because the cathode, this is where reduction takes place. Okay, now we have an electrolyte. So it says define the term electrolyte. Okay, we're not going to waste any more time there. So we have one. So one here, an electrolyte, we can say is a solution of an ionic substance that can conduct electricity. Okay, so it has a conductivity that is quite good. So it's a solution of an ionic substance that can conduct electricity. You stop there. Or you can say it's a solution of an ionic substance. It's fine. Okay, identify the anode in the cell. Choose between P and the ion spoons. It's obviously going to be P. So here it's P3. The anode is the one that is connected to the positive end of the battery. Write down the equation for the half reaction that results in the plating of the spoon. So remember, we're using copper. So we're going to have here, now there's two coppers. Now let's look at this one. It's going to be dangerous if you just jump in without noticing what is going on. Now let's look at these coppers. Now we have these two. We have Cu2 plus going into ions. So you see, you can't take this one because it doesn't go into a solid. It still is in ionic form. So you, our friend, I'm sorry, you are not the chosen one. Where is the chosen one? The chosen one is the one above it, because this one is our chosen one because it goes into a solid when it undergoes reduction. So use these clues, guys, to make sure you don't lose marks. So this is copper 2 plus. This is aqueous solutions plus 2 electrons. It goes to copper, the solid. And you must not use a double arrow. You will be killed and buried instantly. We won't even take you to the morgue because we'll be wasting money for a dead thing. Okay, not a thing, but a dead body, which is you, sirs and Mrs. Or and Mrs., not Mrs. You're not married, you guys. You can't be married. Okay, maybe you are, but it's not expected at this point. All right, no problem. Now it says the polarity of the DC source is reversed. When we reverse the polarity, that means a reduction must take place here now instead of there. Okay. All right. They may even ask you, what should this electrolyte be? You can maybe say copper sulfate if you want. or copper nitrate. All right, copper chloride, whatever you want. Usually copper salts are soluble. So we know that the copper is coming from the solution basically here, because we have no identity of what that electrode is. Okay, now if we reverse this one, it means we're going to start piling the copper here in the end, because now it becomes the negative terminal and that one becomes the positive terminal. That means we're going to corrode those spoons. They'll lose their shine. Okay, not a problem. It says now, how will the mass of the electrode P be affected? Choose increases, decreases, or remains the same. The answer is, well, we know that it will increase, right? Why? Because it is going to undergo reduction. The reason is that reduction will take place in electrode B. All right, not a problem. Now, question 5 says the copper used in this electrolytic cell is not pure copper. It contains a small percentage of zinc. Okay, yeah, which is more like a natural situation, right? You don't really get them pure, so you have to purify them. Now it says write down the name or formula of 2 cations present in the electrolyte. What are you trying to do here? This is going to be the zinc 2+ ions and the copper 2+ ions. All right, so it is observed that the ion spoons are not coated with zinc. Explain this observation in terms of the relative oxidizing strengths of the substances. Well, we know that zinc 2+ ions, remember it's only the ions, zinc 2+ ions are a weaker oxidizing agent than a Cu2+ ions. So you see here, zinc ions appear way below the copper ions in our table 1 there. So you see zinc is right down here. See, these ions are way down here, and then the copper ions are way up there. So this is increasing oxidizing ability. So that one is more likely to be oxidized than the zinc. Okay. So guys, this is how you could attempt to score yourselves the best marks ever. So you see, I answered all over the show, so I'm a crazy guy, so it's fine. Bafethu senizongixolela because yabona ngoku sesilimele manje, sekulimelekile. It's injury time. All right, guys, I hope you have enjoyed the video. Of course, if you spot any errors or mistakes, do let me know, so that those can be corrected, so that no one can be misled by this video if they're watching it. But you will see that most of the times, if I've made an error somewhere, I have a tendency to discover it as I go along, because you see, my brain is forever boiling, so it never stops working. So I have a tendency to correct some things later. As you could see in the previous physics video, I made a big error of a definition that I realized at the very end of the paper. Now, you may have thought, yeah, I'm crazy to really go on and not think about it. So please make a habit of double checking what you're doing. Otherwise, guys, enjoy this video, use it for practice, take this paper and redo it. Even after watching this video as a whole, redo it. You will see that you will get stuck along the way. As much as you have seen what I've done, you will get stuck. And please try to explore other methods as well. Don't limit yourselves to these methods I chose here. I just wanted to get done with this paper within, appreciable amount of time, to portray to you this is how you can go about this exam. And it is doable, because look, if I'm talking a lot of things in between and doing a lot of unnecessary explanations, when you're doing the exam, you're not actually doing that at all. Just keep any analysis and brainstorming to a minimum. But that minimum will essentially align yourself with all of the other stuff that is linked to it, which helps you to remember faster and better. then you become quicker in answering. And otherwise, guys, this marks the end of a video with me for 2022 for physical sciences and mathematics that you have done. So I hope you guys are going to get those distinctions. And yay, Namahlubi, I want that distinction when you do tell me when you finish and your statements come out. I want you to email me your results, because there's a big reward that is for you if you get a distinction either in physics or in maths or both. Okay, of course, this is not to single out anybody else, so anyone who's watching this channel, if you want a bit of a reward, you will send me the results of your what is this, the results of your math and physics. Just send the statement, email it to my email address, which you will find in my channel and some of the videos that I posted recently. And then, of course, you will only get these if you have subscribed to the channel. All right, so if I look and see your results but you're not someone who subscribed in the channel, then you're not gonna get the prize, unfortunately. So do make sure you are a visible subscriber, because there are some subscribers that are not visible, so I don't know who they are. So unfortunately, I cannot be able to do what needs to be done. Other than that, guys, we part in a good spirit, and I wish you all the best during your exams. Remember to stay calm. Remember to pick on the questions that are easy early enough. Remember to pick on the tough ones as well early enough. So for me, I would take apart the the question 8 and 9. The electrochemical cells are usually easy, but if a question starts to become a bit nasty, you can jump it. It's not a big deal. Then the next station is the MCQs. Okay, take down those MCQs because they are usually very easy. And then the next one to take down is question 5, 6, and 7, right? No, is it? Yeah, 5, which is reaction rates, chemical equilibrium, and question 7, which is acids and bases. Those questions can take a toll on you based on the too long high mark calculation based questions. The rest is pretty easy to answer, so that's why those questions are the next one to take down. And then you can go and enjoy organic chemistry last. See our paper when we were students back in 2005. Organic chemistry was the last question, because it's easy to get through organic chemistry, even though it can be quite long and tiring, but you can even answer that part of chemistry even when you are under pressure and you have less time available. It is not usually difficult. Maybe the one that may challenge you is a question on what? It's usually that question on the reaction types. Sometimes you may be asked some very easy to forget questions as to what are the conditions. Hence, if you really want to make your life easy, when you read or practice for organic chemistry, please focus more on the reaction types, their conditions, and some specifics around those reactions, because that is the only technical part of organic chemistry. The rest is fairly easy. Even those technical parts are really doable. You can get more than 50% of the question, even if you're not prepared that much enough. Okay, guys, bye-bye. I will see you next year if you come back, which is not a bad thing. Remember, if you are not strong enough this year, you will still be strong enough for May, June exams. So this channel will still be active, and I will try to upscale the activities included in this channel. I will not only limit it to just exam question paper solutions, trying to revise. I'll probably add in some lessons that I feel may be necessary to solidify your knowledge of the subjects, okay? And if God permits, I will perform a few experiments for you guys so that you can see these things, so that you can understand them a lot better. I found experiments to make the difference, especially on technical concepts in the subject. Okay, guys, enough of the nonsense, enough of the talking. You will hear my voice again next year, even if you have progressed to university and to whatever you'll be doing. If you just get bored someday, just pop in the channel and just go and hear my nonsense there and be entertained. Otherwise, you are welcome in this channel to be a part of it for as long as you want. Good luck, guys, and write well. Remember, eat well, drink, and rest well as well. Make sure you have good sleep. And do believe in yourself as well. And take your confidence with you. Fight to the death so that you do not blame yourself for not giving your absolute best. Hang on as long as possible until it's all done. And may God bless you all. Bye-bye.